Hello guys, we are going live, and on this show we're talking about how to become a good embedded engineer, how to learn embedded systems, what you need to know, and all the little details that you need in order to find the information that you need. So I put together this system, let's see here, where I have broken it down to 13 different steps. And I've updated this list today with some new steps because I think they're very important. And I've organized the list such that it's in chronological order of the things that you need to learn. And the number one thing on this list is marketing. And the reason for that is because marketing kind of opens up everything else for you. A lot of people are asking me, where do I start? How do I plan my studies? What do I need to learn? Do I start with Arduino, or do I start with C, or do I start with something else? And where you really should be starting is marketing, because marketing will show you what it is that is needed in the marketplace. So with marketing, what is meant is kind of reaching out and figuring out what is needed. And number two is building out your team and finding the people that are good at different things, so that you are ready to kind of start thinking about the products you want to create. And the products that you want to create and the things that you're going to learn are dependent kind of on the marketing that you've been doing. Then you do microcontrollers and CPUs. You learn about microcontrollers. You see how microcontrollers work, how you connect them together, how you get everything working. You have tool chains and environments. You have operating system design, schematic design, analog and digital electronics, PCB layout, programming, mathematics, HDL, FPGA, ASICs, documenting and testing, and last on the list is sales. Now we're going to go through every single step on this list, one step at a time, and look at the details of what they actually mean. So the reason marketing is important, as I said, is because it's all about reaching out and maximizing the reach and maximizing how often you reach out. And it's also very much about direct conversations, because you will never be able to figure out what it is that you should build unless you have one-on-one conversations and two-way communication with people. This is what a lot of startups are missing, and it's kind of obvious that it's something you'd never learn when you go to university, because otherwise you would imagine that everybody would know that. But when you ask somebody, what do you offer, most often what you get is they start talking about their product, which has completely zero relevance. What they should be talking about is their offer. You don't need a product to create an offer, but you need a product in order to be able to fulfill on that offer. And product, generally speaking, is kind of, it's secondary, because you can switch it out to something else in order to fulfill the offer, and it's going to be just as well suited to fulfill the offer as any other product of the same type, right? So the first thing you need to think about is creating your offer. What it is, what problem. So offer is about the problem that you're going to solve. When I was a kid, my grandmother used to always tell me, whenever I did something, whatever it was, she would tell me, who the hell would need that? And she actually had a very good point. It took me many years to figure that out, what the point was. But she actually has a very good point, because you need to know, you need to kind of figure out, first of all, before even studying at the university, you need to understand what is needed and how you can create, what is needed first and foremost. And that determines what you would study, the subject you would study, because the subject you would study is actually dependent on the product you want to create. And product you're going to create is in turn dependent on what you discover that is needed in the first place. And But marketing is a little bit more than that. It's about finding information on different sources. And it's not necessarily about asking, because if you would have asked people at the beginning of 19th century or beginning of 1900s, when cars were invented, if you would ask them whether they wanted a car, they would say, well, no, nobody wanted a car, because they were just thinking in terms of horses. And so it's something that you need to discover. It's not something that you need to ask about, but you have to discover it and validate it through by making offers, by marketing in general, right? And that's what proof of concept is about. So proof of concept in terms of marketing is basically validating that the offer is attractive and the offer is needed. And it's an iterative process, but you have to be engaged in it from the very beginning before you actually even create anything else. Because if you start from the end, you will find a lot of resistance along the way, because you have no idea what it is that you're supposed to be creating. It's all about marketing is all about establishing new communication lines. For most people, marketing is basically sending out 5 CVs in every 3 years or 5 years whenever they need a job. That's what most people understand as marketing, and that's what most people do. What you really should be doing is having one-on-one or like direct communication with 100 people a day. 100 different people a day. It doesn't matter how many projects you're doing. It doesn't matter what work you're doing. You should still be always having 100, at least like a standard 100 people a day. It's harder to make more than that. Then you really have to push yourself, but it's possible to make 100 people a day. And if you don't want to do it yourself, you can always get somebody else to do it on your behalf. But it always has to be there, and you have to really push yourself to do it, to contact and communicate with 100 people a day. And it's also about reaching far enough. So if you're not reaching far enough, like you want to reach as far as possible with everything you do, because it's kind of like you establish communication lines with everybody that could be relevant to figuring out like your offer and to improve it. Because it's the people that you communicate with that determine that help you improve your offer. Otherwise, you don't know what it is that you're going to offer. Like you can't start guessing. You can't start thinking that you can't start thinking based on yourself. You have to really just sort of do it based on communication. That's the fastest way to do it, and it will answer you all of your questions regarding what it is you need to learn, where you need to start, what it is you need to study, what it is you need to create. Everything is tied into this basic concept of communicating far enough and often enough. In marketing is also about the fundraising and finding people that. So, for example, if you are in direct communication with potential buyers of a particular offer, it becomes easier to get funding, because now you have an actual proof of concept. You don't have a proof of concept if you just have an idea. So ideas are worthless unless you've been communicating them to people and finding that people understand them and people want them. So if you then want to do fundraising, you should be able to present like a particular exact people that want the final product and are willing to pay for it. And then it becomes easier. So that's it for marketing. That's number one. And by the way, we're doing this show every day at 9 o'clock. So it's going to be every day something new every day, just evolving, and fleshing out the different areas, because there's so much to talk about in every one of these points that it's literally content for many hours. Then number 2 is partnerships and team building. You need to be finding suppliers. You need to be finding good people that can do different things. Like, it's hard to do everything yourself. You need to be training people as well, training people to do stuff that's important. But that comes after the marketing, right? So if you ask yourself, like, what people do I need to have, it kind of comes after the marketing, because once you have done the marketing, you know what people you need in order to implement something, like what skills you need and things like that. Team leadership and bringing out the best in people. That might sound like simple, but it's really hard and can be complicated. But it's something that always has to be there. because people are good at different things and they like to do different things, and some people are really good at something but not very good at other things, and those things need to be brought out. Number 3 is microcontrollers and CPUs, because we are building embedded systems, and embedded systems either use microcontrollers or CPUs, depending on whether it's a small embedded system or maybe a Linux-based embedded system, which is a little bit more complex. And we need to understand, because this is the central thing in almost all smart things today, unless, of course, you go to FPGA maybe, and basically in FPGA you would be creating your own kind of your own CPU, because you are implementing all the algorithms in logic. But to get there, you still need to understand how CPUs work and how microcontrollers work. So microcontrollers are very critical, and it's kind of where everything starts. You pick your microcontroller and you start learning it, and then you can apply. So now you know what it is that you need to create, and now you can pick a microcontroller and learn more about it. Based on your requirements, right? And then once you're kind of comfortable with microcontrollers, and you know how processors work, how memory buses work, how you connect them together, you learn the tool chain and working environment. What tools do you need? How do you build software for microcontrollers, programming editors, compilers, file manipulation tools, using Linux, because Linux is something we use on the embedded systems, so it makes sense to use Linux as a workstation as well. Then to develop firmware, so you need to program the microcontrollers, and in order to do that, you need to develop firmware. And in order to develop firmware, you need to understand operating systems, because you maybe not always use an operating system, but you still have to code it in a way that makes sense and in a way that is scalable, right? So how do you do that? You need to understand operating systems. There's a lot of resources on operating systems. Operating systems have been around for ages, and they've become increasingly more complex. In many cases, we can reuse Linux, but in more smaller devices, battery, like devices that have to consume very little battery, they need to have small microcontrollers that need to implement some of the things that operating system implement, but do so in much more simplified way. But you need to understand how it works in order to do that. And operating system design, by the way, you can learn that without actually having a PCB. So you can learn this with QEMU emulators, software that even if you compile Linux as a user space Linux, there's something that's called user space Linux, and you can actually build Linux kernel and run it in user space. So you can experiment with it, play with modules and all that kind of stuff. You don't need any actual hardware to run it on. You can run it as a user process. So it's really useful. But once you kind of understand that and you feel comfortable with that, and you feel like you want to go to the next level, then you design your schematic, right? So now you can start creating your product. And when you do your schematic design, you will go back naturally to microcontrollers and CPUs, read their data sheets, figure out how you connect things together, go to tool chains, improve your work environment, get better tools for schematic design. Maybe you get Altium, maybe you get KiCad, maybe you get Eagle, whatever it is that you're using, and then you learn how to create schematics. So how do you connect everything together? How do you make your libraries? How do you find your components? And things like that. And maybe like in the beginning, you don't need to really understand electronics that deeply, but as you progress, so you can build simple schematics rather easily, but as you progress, you really need to start learning analog and digital electronics. Because this is the field that's gonna tell you what capacitors you need to use, how you build electronic and analog circuits, how you make them work together, how you control peripherals. Like you understand really then how to control peripherals on the CPU, how you can get different signals, filter them. Like if you have a PWM signal, you can filter that to get an analog signal, and reading analog signals, amplifying them, all of that is in analog circuits. Digital logic, power circuits, very important because power is everywhere in every single device. You need to have efficient power circuits that are stable and that don't create overly much noise. and electrical simulation. So you need to you'll start simulating things. So you can actually start designing your schematic and then do electrical simulation to verify the schematic without actually making a PCB, right? And you can even do, like with electrical simulation, you can even write code in C and test that code in a simulator. So you can actually develop a device in C and implement that in a simulator. So you extend your simulator with a new device, and then you can actually program it and experiment with it, right? So with toolchains, you maybe start a little bit of programming there. You start learning compilers, but you kind of just briefly, right? But you can start with simulation and kind of get to see the effects of your circuit that you're building before you actually produce the final product, right? And then once your schematic is satisfactory, you go to PCB layout. That's a whole area in itself when it comes to actual mechanical layout. How do you determine how many layers you're going to have? How do you route your power lines? How do you separate things into different analog and digital sides? Maybe you put components in different, like group them together in different places. And all that is kind of like electromagnetics, the study of electromagnetics, a lot of physics, and it's a science in itself. Like there's so many resources. If you register for free at switchembedded.com, you actually get links to different books that deal with a lot of this stuff in detail. There's a lot of resources available to you that show you where you can learn how to do this. Signal integrity, magnetic simulation, there's tools for that as well. In Altium, you have signal integrity. You can also do different types of magnetic simulations where you can determine how signals travel through a trace on a PCB. So you've designed your schematic, you have basic understanding of operating systems, you have basic understanding of microcontrollers, tool chains, different PCB design tools, operative schematic analog PCB layout, and now you have produced your PCB, right? So now it's time to start programming it. And this is where you learn software architecture, you learn debugging your software, you learn static analysis of the code to make sure that the code looks good and doesn't have obvious bugs. Testing for correctness, for example, Valgrind is a tool to test for memory leaks. And networking, communication, different types of different languages. You would use C most of the time. Sometimes you might use Python. Sometimes you might use some new language, for example, Rust. Programming is basically about software architecture. That's the main thing in programming. And programming languages kind of come after that because you start really with the conceptual understanding of software architecture, and then you implement that in a particular language. So language is kind of like the details of implementation, just basically translating your conceptual representation into something that compiler can compile into machine code. So now you can program your PCB. Now you have, when you do programming, you will go back naturally to microcontrollers and CPUs. You will work with tool chains. You will program different algorithms that come from operating system design. You will work with your schematic to implement your software. You will go back maybe to your simulations and maybe simulate things based on the signals you're going to be generating through programming. You will go to your PCB layout to figure out where you're going to test things, like where you put the test points, right? So you might use a scope and test output from your board as you are programming it, right? But programming takes you sort of a lot of steps along the way, but eventually you hit this ceiling where to get to the next step, you need to understand mathematics. And so we get to mathematics. And mathematics, whenever you're working with signals, it makes a lot of sense to convert the signals into mathematical representations. And we have different representations for that. When we work with digital circuits, we have the discrete representations, and we have formal methods to develop dynamics and process signals in discrete domain. And as you're working with signals, as you're working with your analog circuits and you're measuring things, you have noise and you have to And maybe you're measuring some variables, but not all of them. You have to predict some variables, and you really cannot do that unless you understand digital signal processing. What you see people do when they don't understand digital signal processing is that they would, for example, implement a complementary filter, and they will just sort of play with the coefficients and determine based on trial and error how the coefficients should be set to achieve sufficient filtering. But that's very time-consuming way, and you don't need to do it that way. You can just design the filter in a software like MATLAB, for example, and then just translate that into C code using the Z-domain equations, which translate into difference equations in C code. And control theory and controller design. So we have filters and estimator design, which gives us measurements, and then control theory and control design gives us algorithms for actually controlling something on the outside world. And embedded systems are typically used for control. So they do some kind of control of something based on sensor data and based on some control criteria. And to achieve that, like, you can tune, like people do PID tuning, like PID controller tuning by trial and error. But control theory really deals with how you do it mathematically, so you don't have to waste time doing it by trial and error. And when you are when you kind of get into control theory, you really need to understand linear algebra, because control theory is based around state space models, which are matrix models, and even estimator design as well. When you're working with Kalman filters, for example, you're working with matrices and you're working with vectors. And linear algebra is all about matrices and vectors. So understanding linear algebra is extremely useful when you're working with all of this kind of stuff, all of the signal processing stuff. And finally, we have Boolean algebra, which kind of relates more to logic, and it allows you to it allows you to simplify complex complex logical expressions that you might encounter when you do programming. With Boolean algebra, you can simplify them, and with Boolean algebra, you also Boolean algebra is the main thing that you use to kind of simplify logical design, and this is done automatically for you by hardware description language compilers. But at the bottom it's kind of linear algebra. So let's say you have programmed your microcontroller and everything is working, but you want to make it a little bit faster. So then you need to understand FPGAs and special circuits that you can build specifically for your solution. And FPGAs. The HDL, hardware description language, translates a lot of like programming concepts directly into logic, and so a lot of things happen at the same time, because in logic it's basically just you have a clock, and the clock clocks everything at once, and everything can happen at the same time. And some things might take several clock cycles, but it's still a lot faster than executing things instruction by instruction by instruction. And HDL is what is used to actually create your microcontrollers. So when you go back here, when you start learning HDL, you basically go back to your microcontrollers. You work with tool chains. You work with maybe you don't do so much operating system design unless you also interface from your microcontroller to the FPGA, and then schematic digital circuits, definitely PCB layout, except now you're maybe going to be creating like a chip layout, which is a lot more complex than PCB layout. And programming, you need to understand programming, definitely, because you're going to be programming in hardware description languages. In mathematics, Boolean algebra, just simplifying things in mathematics so that you can create more efficient circuits. So everything ties together. So every step of the way ties into all the previous steps. So it kind of makes a lot of sense. And then finally, as you're developing your product, so the goal of this is basically developing your product. So you're working with embedded systems, but there is no it makes no sense to work with embedded systems unless you're actually creating something. And the ultimate goal is obviously to create your product. So you've started with marketing, you moved through the whole design process, and now you have to document it and make sure that it's working and package it up for delivery to the people that you've been talking to in step number one, right? So now you go to once now you document it, you make sure that everything that you have in the manuals, and then you go to sales, and this is kind of the last step, right? So if marketing was the sort of the tip of the airplane, like the tip of the supersonic airplane that punctures through this shockwave, then sales and the customer relations would be the afterburner that comes at the end of everything and kind of propels this whole thing forward, right? So sales is different from marketing because sales is more about working with existing customers and kind of making sure that they can apply the products and make use of the products better. Sales is about education. Sales is about a lot of different things that help push the product forward. And it's also, you'll be discovering new products, new ideas, maintaining regular communication with existing customers, arranging events for existing customers, and kind of like tying it back. So when you get to step number 13, so you're doing all of the steps all the time, right? But when you get to step number 13, you kind of tie it back to step number 1. And so that's it. And if you want to learn more, I have a Switch Embedded Academy where I'm making courses. If you want to do one-on-one coaching, we can do that as well. You can go to switchembedded.com/book-call. So switchembedded.com/book-call. And you can, if there's no time slots available, you can also sign up at switchembedded.com/free. And then when you sign up, you'll be invited to live events. So when I do interviews, I'll invite you. When I do workshops, I'll invite you. So I do regular workshops where you can ask questions. You can bring your own code. You can share your screen as well. So it's very practical to do it in a workshop setting, and you'll get an invitation once you sign up. So just go there, go to switchembedded.com/free, sign up, and I'll see you later.